Hello, it's Ahmed Medhat, and I'll be showing you a demo of my team's project, the Tomasulo algorithm simulation. So just at the beginning, let me walk you through the code, how we approached this simulation. We made a separate class for each entry in each of the Tomasulo architecture components. For example, the reservation station. The register file will have each entry each entry is represented by this class register in the register file. Each entry in the load buffers is represented by this class load buffer, and so on. We also created a class instruction which will represent a single instruction too, and at the end we created the main class, which is the simulator. This will have an array list of all the other classes, like array list instructions will show all the instructions in the code, and the array list load buffer which load buffers which will have each load buffer. So each array list of these is considered a component from the Tomasulo's architecture. The simulator class also has some attributes that represent the number of cycles for each operation and the clock cycle, when is the simulation done, and so on. After that, in the main method, we initialize a new simulator which will take the number of cycles for each operation as an input, and the order can be found here in the constructor. Also, we initialize all the components. How many registers do we need from F0 to F10? For example, here we can change the numbers and change the number of components we need, or the number of entries we need for each component, for the register, for the load buffers, the stored buffers, the resist stations, and everything. Then comes the loop that takes the input code, and the main loop here. This main loop represents the whole simulation. So each entry, each iteration in this loop is a single clock cycle, and inside the loop we can find different blocks of code which are described by a comment at the beginning of each block, which will show or will tell what exactly this block does. So these blocks are generally just fill the components of the Tomasulo architecture, fill the reservation station, the load buffers, the stored buffers, and the register file according to the algorithm. So for example, this one writes the finished results and resets the buffer. This one decrements the time for the executing loads, executing stores, and executing ALUs, which are instructions in the reservation station. So each block will do a job as described in the command. So now let's take a small example. We can run the code here. Let's maximize this a little bit. So let's take a small example. For example, we can say multiply. By the way, we must enter the data here accurately, because it's defined as mul.d and all capital letters, so it must be entered accurately for the code to run properly. Also for the name of the registers and for everything, so that data entry is very important to be accurate. So we can say mul.d. He will ask me about the first register, so let's say the result is in F0, and the first register is F1, the second register is F2. Add more instructions, yes, and then we will say let's put an add operation, for example, that will depend on F0. So let's say it will store in F3 the value of F0, add it to F4, and then let's add another one. Let's make a totally separate instruction. So instruction name, let's say add F7, F8, and F9. So let's say this is enough for now, and let's see what we can get here. So in the first cycle, the cycle updates will show what happens in each cycle. So this cycle has an instruction that has been issued, the first instruction, the multiplication, and the register file will have F0 depending on this value coming from this M1, and the M1 is here it will say the first number 5 is the time remaining for this instruction to finish executing, and M1 is the number of, or the name of this spot in the reservation station. Multi is the instruction. This is the VJ, the VK, and this is the QG and the QK. And since all the registers are available already, they are not waiting for anything, so the VJ and the VK are with the values of the registers, and the QJ and the QK are 0. The load buffers and store buffers are empty, so it tells me type any letter to proceed. Let's type anything and proceed to the next cycle. This is cycle 2. So we have one instruction, the old one executing, and another one issued. Also the register file is updated, that A1 is here in F3 now, and this instruction add, we can see now that the VJ is not here, it is 0 because it still depends on M1, so it's the QJ will be M1 until M1 finishes execution. Actually it still needs 4 more cycles, so let's just proceed with some cycles until we reach here, for example cycle 6. We can see in cycle 6 that this instruction finished execution. Then it will write in the coming instruction. So if we proceed, we can see here in cycle 7 the result written back. So when the result is written back, now we can find that this value is here in the reservation station for this add. We can see that the value is already here, and it's not in the QJ anymore. It's now in the VJ. So we can just proceed until the end of this code. Okay, so we have ended this code, and the last cycle here is cycle 10, where the value of the last instruction, the add D, is written back to the register file. Okay. So we can change, as we said, the number of cycles for each instruction, and so let's take, for example, the lecture example here, because it was actually explained in details in the lecture, so we can compare at all the times, all the cycles, the values in the register file, the reservation stations, and the load buffer. So let's get here to cycle 1, and let's write this, but first let's adjust the simulator, the cycles for each operation. So we can say this was 10, I think, and these are 2, and the division was 40. I think this is correct. So let's save this and let's run and enter the new code. So let's do this. LD F6 52 or 2. Yes, one more instruction. LD F2 44 R3. One more. Mul D F0, F2, and F4. Another one. Sub F8, F2, F6. Another one. div.b, F10, F0, and F6. Another last one. Add E, F6, F8, and finally F2. No more instructions, and let's see. So this is cycle 1. We have L1 in the register file, we have this in the load buffers. Let's check. We have L1, we have this. So let's proceed to the next cycle. Let's type anything and proceed to the next cycle. We have L2 and L1, we have these. We have L2 and L1 here, and we have these in the load buffers. So let's proceed to the next cycle. We have this in the reservation station, still the same in the load buffers, and another one here in F0. Let's proceed. This appeared here, this appeared in the reservation station. We can see that the VK and QJ are the ones filled here with RF4 and L2. The QK is empty and the VJ is empty. Let's check. Yeah, the QJ is empty and the QK and the VJ are empty, so these are the same values. So let's take a random cycle, for example. Let's just proceed to a random cycle. Okay, I don't know what's this. This is 14. Okay, this is cycle 14. Let's check cycle 14 here. So in cycle 14 we have M1 and M2. Yeah, M1 and M2, and the adds are all empty. Oh, the adds are all empty. We have M1 and M2 here, so the adds are all empty. We have M1 and M2. The timings are correct. This still has one cycle to execute. The QG and QK are empty, are zeros. The QG and QK are empty. Here the QJ is M1 and the VJ is empty. The VJ is 0. Okay, so it's the same output. Everything is going alright. We can also proceed until the end to see the number of total cycles. So we can continue like this. So this is the last cycle, so the total cycles for this are 57. Also, if it's not convenient to just press buttons to continue cycle by cycle, we can just comment these lines in the code, the last lines here, these two lines. If we comment them, all the output or the whole number of cycles will appear once, and the whole result will appear at once without need to proceed cycle by cycle.